Okay, welcome back. We're still in section 2.2, but we're now going to look at example 2, which takes a look at still the disk method, but we're going to now rotate about the y-axis. The last example we looked at was one where we rotated about the x-axis. And so things are still pretty similar. Just like in the last example, we still want to start by sketching a graph of our region. So we'll start with that. All these problems you want to sketch the graph. And so I'm going to sketch y equals 1 first. There's 1. There's y equals 1. Then we have 2, 3, 4, 5, 6, 7, 8. There's y equals 8. And then we have y equals x cubed. Y equals x cubed. We know that y equals x cubed goes through 0, 0. 1 cubed is 1. So we have the point 1, 1. And then 8, what cubed is 8? Well, 2 cubed is 8. So when we plug x equals 2 in, we get 8. So that's our intersection up there. That's the point 2, 8. We have 1, 1, and then we also have x equals 0. That's the y-axis. So this cubic function is the other boundary, and so we basically get this region here shaded by red. And this is one where we definitely want to go left to right. And so I'm going to, again, draw in that representative rectangle here. Drawing that representative rectangle, and now our thickness is a dy because it goes vertically like the y-axis. And we are rotating about the y-axis. So when we rotate about the y-axis, now we're going to get, with this, think about this representative rectangle. We rotate about the y-axis. Now we get a disk that looks like this. There's our disk. Make that look a little better. All right. And so again, the thickness there, in the last one, the thickness was dx, but in this case, our thickness is dy. And now our radius, which is right there, that's our radius. Our radius is no longer y, our radius is now x. It's that horizontal distance, it's x. And so that's why the formula looks like what we have up here in equation 2.4. It's now our g of y function, what x is equal to. And so if you take a look at that curve, this curve on the right, that signifies how far the radius is, that's our curve y equals x cubed, but we want to solve that in terms of x. So that's going to be x equals the cube root of y. So our formula here, our volume, is going to be the integral of pi times the radius squared, but dy this time, right? This is our radius. The radius is squared, which in this case is x, so that's the integral from, we have pi, and r in this case is x, because r is going in the horizontal direction. So it's x squared dy. And because it's dy, we want to think about where y is going. What is this representative rectangle is going between y equals 1 on the bottom and y equals 8 on the top. So our limits are going to go from 1 to 8. And again, we have the same problem we had in the last problem, that this is in terms of y, so we need to change that x to be in terms of y. So we have the integral from 1 to 8 of x, which is the cube root of y squared. And if we write that as a power, that's probably the easiest way to think about it. So what power is that going to be? It's going to be y to the, hopefully you said 2/3 power, because our index there on the root is a 3. So it's 2 over 3, power is 2, dy. And then that's a pretty simple integral, right? So take the antiderivative, you add 1 to 2/3, you get 5/3. So you get y to the 5/3 divided by 5/3 or multiplied by 3/5. And evaluated from 1 to 8, you get 3 pi over 5 times 32, because y to the 5/3, cubic root of 5 is 2, and then 2 to the 5th is 32, minus 1. We plug 1 into y to the 5/3. And so 32 minus 1 is 31. You multiply that by 3, you get, what's that, 93? 93 pi over 5. That's our volume. Okay, so hopefully that made sense. You've now seen the disk method work both ways when rotating about the x and the y axis. And we got one more video to go over in this section. We also need to look at what happens when we then rotate about the x or the y axis, but there's a hole in the middle. So it doesn't look like a disk, but it looks like a washer, if you will. So we'll see you in the next video for that one. Thank you.